So in this lecture segment, we're going to dig a little deeper into free energies and determining whether a reaction is spontaneous or not. So let me go to the lecture objectives here. So the lecture objectives for this segment are to relate chemical spontaneity to both equilibrium constants and free energies. Recall that we already looked at spontaneity using equilibrium constants. We looked at the Q to see if that was above or below the K. But we're also going to show how that's related very much to free energies as well. They're just different ways of talking about the same underlying phenomena. And we're also going to be looking at calculating the free energies at non-standard states. All right, so free energy changes that are not at standard state. Remember, the delta G standard state tells us the direction of spontaneous reaction when the reactants and products are present in the standard state. Concentrations 1 atmosphere, 1 molar at 25 degrees C. But usually the reaction mixture is not at standard state. We have some other concentrations. And so how do we predict the direction of a realistic mixture, not standard state concentrations, using thermodynamics? We need to have some relationship between the free energy of the process and the free energy of the process at standard state. So what do we know? Well, we know that Q less than K, that means we'd have a spontaneous reaction to products, right? But we also know that delta G is less than 0 also means a spontaneous reaction to products. So those are two different numbers we can look at. One is a number that is positive or negative, delta G. The other is a number that is less than some other number. So we have one that's positive and negative and one that's less than some ratio. And so are they related? The answer is of course yes. And it turns out that given a reaction with the reaction stoichiometric coefficients, remember that reaction quotient, and this is the reaction quotient at any concentration, not just the equilibrium concentration, that's the distinction between K and Q. Then the free energy is equal to the standard state free energy plus RT log Q. And we won't prove that, but we can look at it, squint at it a little and see why it makes sense. So if Q equals 1, then the delta G is equal to delta G standard state, right? Because if we have, remember the Q is defined, each of these concentrations are defined in terms of the ratios at 1 molar. So if everything's at 1 molar, Q is equal to 1 molar, and therefore delta G has to be the delta G standard state, right? Because Q is defined in terms of standard state and delta G standard state is defined in terms of standard state. So it makes sense that when Q equals 1, then the delta G has to equal delta G standard state. Because we made those definitions. So it makes sense there has to be some relationship between the free energy and the free energy star. And so we know that that relationship has to hold. What about at the other concentrations? Well, let's look at this graph of free energies versus equilibrium. And we're going to spend a little time in here because this is really important to get right. So on the y-axis, it's the total free energy of reactants and products. So that's the total free energy of the entire system, all the molecules in the system. And so when we start out, then when they're all reactants, we have pure reactants, then the free energy is going to be the free energy of the reactants. If we reach the state of pure products, then the free energy is going to be the free energy of the pure products. Now, we know that there's going to be some reaction to reach an equilibrium mixture, right? We know that just from thinking about Q and K, we know that if it's pure products, then Q has to be essentially infinity, right? Because there's no reactants, there's all products. And therefore, K is going to be greater than, Q is going to be greater than K. So we know that there has to be some sort of spontaneous reaction backwards from 100% products. And we also know that we're not going to have entirely all reactants, right? Especially if this is a reaction with a delta G that is greater than, less than 0, it has to move forward. Also in that case, the Q over here, Q would be 0, right? If it was all reactants and no products, so there's nothing on the numerator. So it's going to move from a state of the pure reactants of pure products and keep reacting until it reaches some point where it's at an equilibrium mixture. And so it spontaneously reacts away from pure products until there is some of products and some reactants. In the same way, if it's at all reactants, it'll react all the way spontaneously until it reaches that point. And any reaction that moves away from that point, that minimizes the total free energy of the system, is going to be non-spontaneous. So that, and remember, so a couple other points on this. So some more points in this graph. This graph shows at a single temperature and pressure. That's important to notice, but at different compositions. So there will be a different free energy at each composition because along each way you have enthalpy and entropy that change as you have some of the reaction going on. Only one composition will be in equilibrium. That will be the one with the lowest free energy. Systems try to minimize the free energy in order to they try to minimize the free energy in order to maximize the entropy of the universe. So the system will react in some combination of reactants and products until it reaches the equilibrium mixture. Another thing to remember is that if we have pure reactants and products, it will always react to make just a little bit of one or the other. If delta G is much greater than 0, there will still be just a little bit of products at equilibrium. A way to think about that is a solubility, right? In solubility, the free energy is definitely tilting toward, if it's an insoluble compound, the free energy is definitely tilting towards having solid rather than the ionic compound being in solution. But there's always just a little bit, even if it's very low solubility, there'll be a little bit of the products of that dissolution reaction in the solution. So that can be understood by looking at this. If you think about the reaction about K versus Q, if it's all reactants, then K has to be 0, and that can't be right. The Q has to be 0, and that can't be right because Q will be less than K then.